Okay, cool. Yeah, thank you everyone, and thank you, Alan, for inviting me today. So as Alan mentioned, I'm a PhD student in the energy graduate group here, and I study the life cycle impact of electric vehicle batteries. And specifically, I researched the impact of lithium extraction and then also end of life management and who is involved in handling end of life batteries and how they get collected and processed and recycled. But today, I think we're going to focus mainly just on giving an overview of the life cycle of electric vehicle batteries. In general, can you give like a show of hands of who has heard of life cycle assessment before? Did you guys cover this already on Monday? Or no? Okay, cool. And who has heard something about the supply chain or recycling of electric vehicles? Okay, so like more or less, yeah, I think at the moment, I think it's a very hot topic. And a lot of people talk about like, are they better than regular cars? Are they worse? Can they be recycled? And I think hopefully after today, you'll have some understanding of generally what the key materials are in electric vehicle batteries, what the sort of status of recycling is, how they might be reused, and then also some solutions to make them more sustainable from a life cycle perspective. So to start out, I'm going to give a brief overview of what life cycle assessment is, and then I'm going to explain generally the materials and recycling of batteries, and then I'll talk more specifically about the steps in an LCA because it's kind of complex and would be probably really boring to learn about in the abstract. So life cycle assessment is the evaluation of the environmental and also can be economic burdens caused by a material, product, process, or service throughout its lifespan. So that includes the material and energy used to create the product, and then also waste and emissions generated throughout the different phases of its life cycle. And people use life cycle assessment primarily to compare alternative products, for example, to compare a gas-powered car or an electric vehicle, which is what we'll focus on today. But you can also use it to compare different production pathways. So if you use this method versus that method to produce something which is more sustainable, and also to identify hotspots in a system. So to identify if there's a certain point in the production process that's generating a lot of carbon dioxide emissions or using a lot of water, and then a company or a policy might choose to focus on that part of the process to make it more sustainable. So this is a high level of what that might look like. So the phases that generally can be included in a life cycle assessment include the raw material acquisition. So that would be, for example, mining of ore, the materials manufacture, which could include refining and then also kind of producing component materials. The product manufacture, where you're assembling the different components and materials into the product that you're studying. The use phase, so for an electric vehicle, that would be when you're actually driving and using the car. And then the end of life. So that could be, it could go to a landfill or it could get reused, in which case it kind of, the life cycle kind of plugs back into that use phase. Or if it gets recycled, then you look at the products of the recycling and those kind of get plugged back in as raw inputs to the production process. Also, I like to, when I'm talking about electric vehicles, so everybody thinks that I like hate electric vehicles. I don't hate electric vehicles, and it's important to consider all of this in the context of oil extraction and gas-powered vehicles and what the impacts of producing that are. So anything will have an impact. Electric vehicles are no different. And I think it's really important to understand what those impacts are and try to make them as sustainable as possible. But it's not to say that they're worse than what we have at the moment. So are there any questions before I get into the actual specifics of electric vehicles? No? Cool. And if anybody has questions, just feel free to ask them throughout. But yeah, generally, this is a graphic from Redwood Materials, which is a battery recycling company in Nevada, that I think illustrates the complexity of this whole supply chain pretty well. But in general, some of the key metals in electric vehicle batteries are nickel, cobalt, and lithium. The nickel, as you'll see, is largely mined in Australia, Indonesia, and Russia. I think in Canada as well. Lithium primarily from South America and Argentina and Chile and Australia, and then cobalt from Australia and the Democratic Republic of Congo. And at the moment, almost all of those materials are shipped to China and refined in China, and that's where the actual inputs to the battery production process are created. Those are then manufactured into the battery cathode, which is, I'll explain that in a moment. Most of that takes place in Japan or elsewhere in Asia, and then the battery cathode is shipped, and the battery cells are shipped to where the actual batteries are produced, which does take place in the United States and elsewhere. So that's what this is all indicating. So lithium, taking a step back, lithium ion batteries are a technology that are also used in cell phones and computer and consumer electronics. So for example, laptops, and they have a variety of different metals in them. So they're made, generally, there's an anode and a cathode. The anode is made out of copper and the cathode is made out of, wait, no, other way around. Anode current collector is made out of copper and the cathode current collector is made out of aluminum. And then the cathode also has a lithium and then a compound that's made out of cobalt, nickel, manganese, or can also have iron and aluminum in it. And generally, the batteries are defined by their cathode chemistry. So if you hear people talk about an NMC battery, that refers to a lithium ion battery that has a cathode made out of nickel, manganese, and cobalt. And the material composition of the cathode affects what the environmental impact of producing it is, as well as things like the energy density and performance. So now I'm going to talk a little bit more about how some of those materials are produced. This is an image of a lithium mining or lithium extraction operation in Chile, I believe. And essentially how this is produced, this is called producing lithium through evaporation. And essentially they flood large evaporation ponds with water, and then they concentrate the lithium just by letting it dry in the sun. So it moves through the different evaporation ponds and then ultimately is concentrated enough that they can produce lithium carbonate or lithium hydroxide using chemical processing. So this, generally the energy intensity and greenhouse gas emissions of this process are fairly low because most of the heat is just coming from the sun. However, it does use a substantial amount of land and also impacts the water availability in the region. And yeah, Alan.
Where's the water coming from? Is it just like
It's pumped from the groundwater.
Oh, it's groundwater.
Yeah.
It's not like seawater.
No, so the brine, so there's the brine that is used that like is what the lithium is extracted from. And that's not fresh water. That's a minerally water that would not be able to be consumed. But then I think there's fresh water. I know that fresh water is used and it impacts the ground table, but now I'm confused about how. But generally, it's the water is pumped up from the surface, from the ground water table to the surface. Cobalt is another really key metal in the cathodes. This image is taken from the Democratic Republic of Congo, and that's where approximately 70% of the world's cobalt is currently produced. And this is probably the metal that gets the most attention for being destructive. Something that people talk about quite a lot is the presence of artisanal mining in the Democratic Republic of Congo, which is where cobalt is frequently mined by hand and kind of in smaller communities who then sell the cobalt to other people. But often this is done without protective gear and is known to employ child labor. And so this is a pretty large issue in the battery supply chain. But generally, even in the industrial mines, they still have pretty negative environmental impacts in terms of sulfur pollution, which is really toxic for the communities nearby, and then also uses a lot of energy to refine the cobalt into cobalt sulfate. And then the other big one is nickel. Nickel, the environmental impacts that are generally of concern are the habitat destruction and also sulfur oxide emissions that are created when the nickel is refined. So some other materials on the battery besides the cathode active materials are graphite, which is used in the anode, copper, aluminum, which is also used to package the battery and also in the vehicle. So that takes a lot of energy and to refine as well. There's a binder material, electrolytes, and then solvents for the cathode slurry preparation. So these are generally, when I present a life cycle assessment of the battery, we can talk about more the impact of these compared to cathode active materials, but generally the cathode materials contribute the most substantial amount of the environmental burden of the battery. So that's why we tend to focus on those.
Sorry.
Yeah.
Question. Is the current collector, is that the thing that the electrons are basically going through?
Yeah.
That's the complete circuit?
Yeah.
Okay. And is that like, do you need a lot of that?
I should have the weight on here.
I just don't know about that.
I don't think it's like, I think by mass, it's a pretty small portion of the battery. Okay, so once the cathode, once those different cathode materials have been produced and refined, they're turned into a cathode powder using a co-precipitation process that requires a lot of heat, and then calcination that also requires electricity. So then after the cathode is produced or the cathode powder is prepared, it's used to produce the actual cell. So that consists of preparing a slurry, preparing the electrodes, assembling the cell, and then cell conditioning. And the cell assembly process has to take place in a dry room, which has to be controlled, very carefully controlled for humidity. So that's one of the main energy consumption requirements during that part of the process. And then in addition, it requires heat for the drying. And finally, the impact of cell production in life cycle assessments about this has been found to decrease over time, or estimates have decreased. And that's largely because the factories are much larger and can operate at a higher throughput. So if a lot of the energy use is being used to control the climate in the factory, if you're producing a lot more batteries, then the impact per battery is getting less as they see a higher throughput and there's more demand for the batteries. Cool. Okay, so the in-use phase for the for an electric vehicle depends on the fuel source that it's using to charge. So the actual, one of the benefits from the use phase perspective is that as the car is being driven, there are no particulate or local pollutant emissions because you're not combusting everything. So there's no NOx emissions or particulate matter that's emitted where you're actually driving the vehicle. And this, when you're looking at something like an electric truck, for example, this can have a pretty substantial impact by kind of clearing up air quality around transportation corridors. The actual greenhouse gas emissions generally from the use phase, meaning like from the point where somebody buys the vehicle until the point where it's retired, depend on what the energy source is. So in this LCA was done in 2013 and found that it has a 12% benefit compared to gasoline if it's charged on an electric grid that's being powered exclusively by natural gas. And then they're actually, if it's fueled by a grid mix that's mainly dominated by coal, the emissions can actually be higher than a gasoline powered car. But I think this is essentially a baseline. And then as the grid becomes cleaner and there's more renewable energy on the grid, those use phase emissions are expected to decrease to be a pretty unsubstantial portion of the overall life cycle impacts. So that's kind of why we tend to, even though at this point, the use phase is a pretty substantial part of the overall impact, that's why a lot of the focus is on the battery production, because that's where it's going to be harder to get the emissions out of. The life cycle impacts also, when you're comparing it to a combustion engine vehicle, also depend on the battery lifespan. So if the battery is produced and then you're able to drive it for 100,000 miles, then it has a 9 to 14% reduction in greenhouse gas emissions compared to a combustion engine vehicle. Whereas if you're able to drive one battery 200,000 kilometers, the benefits increase to being 27 to 29% lower. Are there any questions? Yeah.
How is that set? Is that just like based off your average gas car in terms of like miles per gallon probably?
Yeah, I think that for this study, they were looking at the kilometer, like per kilometer driven, I believe, and they compared two cars that were a similar size. So then they kind of go through the life cycle analysis process that I'll talk about later, but you quantify what the inputs were to produce and then fuel the combustion engine vehicle over its lifetime, and then compare it to the impacts of producing and fueling the electric vehicle. Okay, so at the end of life of a vehicle, this is kind of an interesting area because the first mass-produced electric vehicle was the Nissan Leaf, and that came out in 2012. And so electric vehicle batteries really have not started retiring at a large scale. And so a lot of the data about this, for example, the data that it will have 80% of its original charge capacity left at end of life is kind of an assumption that we're making. But in reality, it's going to depend on a lot of things. For example, if as the range of cars gets longer, yeah, go ahead. Yeah. Yeah, I think that's just so that it's just a more like accessible thing for people to imagine, but it would be more accurate to measure it in cycles. But again, that's it also depends on driving patterns and driving behavior. And then the other thing that will influence this is the battery will be discarded basically when the driver decides that the range is no longer acceptable to them. And so if the car had a range of 80 miles to begin with, probably that's going to happen much sooner than if you're starting out with a range of 300 miles. And then, does that person decide that they want to get a new battery or trade in their vehicle when they have 250 miles left, or when they have 200 or lower? But in general, the premise here is that it's a much more demanding to fuel a vehicle than it is to store energy as a stationary storage device. So if the battery's fueling a vehicle, it has to charge and discharge very rapidly. Whereas for something like this is a second life battery here on campus. And this is just programmed to charge during the day and then discharge the battery at a constant rate from 5 to 8 p.m. So generally, the idea behind repurposing the batteries is that even if it's not suitable for a vehicle, it could still be useful in another application. And people expect that this will extend the usable life of the battery by 7 to 10 years. But that's also something that's still currently being studied, and it could end up being longer or shorter. So after it's reused, or even if it's not reused, it could, ideally, it will be recycled. Yeah, go ahead.
What percent of like the like not useful for the
I think generally, at least the minimum, I think, is 60%. I know at least for Repurpose Energy, which is the lab that was doing that here, they had batteries that were between 60 to 80 or 90%, and then they would reconfigure those so that they'd have a more even distribution of degraded batteries. Yeah, and so then it's not really expected that they're going to end up in landfills because they're very large and very difficult to transport and very difficult to remove from the vehicle. And so it's not really like a laptop battery or consumer electronic battery where somebody might just throw it in the trash. But you do want to ensure that they are recovered and recycled, and that the materials are recovered in a usable form as much as possible. So these are just some pictures. This is a picture of a utility scale repurposed battery installation, I think. This is in Southern California from B2U, which is a repurposing company. But they can also be used in commercial applications. And right now it's in the startup phase. Generally the industry is. So there are a few startups in California and research projects that are being funded by the California Energy Commission to get more data on what the performance of the batteries are when they're repurposed, and then what the lifespan is and how quickly they're degrading when they're used in that application. So for recycling, the first step is collection and transportation to a facility. And then most of the recycling companies that are being announced in the United States will use a combination of mechanical separation and hydrometallurgical recycling. So the first step is that the batteries are essentially shredded and ground, and then the metals like copper, aluminum, and plastics are separated, and the cathode materials are produced in a black mass. So essentially, I'll skip ahead to this where I have a picture of it. So this is the output of the shredding process, and those materials can be recovered using regular scrap metal recycling infrastructure. This is the black mass that contains the different cobalt sulfate, manganese sulfate, lithium, and nickel. And then that is refined further using hydrometallurgical processing. And that's basically a chemical processing step that can recover the metal sulfates, ideally in a usable form so that they can be reused in battery production. Without that added step, it's still useful and you still get the metals recovered that are more typically recycled. But the more complex metals like the cobalt or at least the lower value metals like the manganese and the lithium are more likely to end up in a slag and be used in cement production rather than actually being recovered to the point of being usable in a battery. So yeah, like I said, this is the process that most companies in North America are using. They claim on their websites that they recover 90 to 95% of the materials, but they're pretty vague about their actual processes and the details, and so it's hard to know whether that will happen. Generally, how many materials are recovered and what the output is determined more by the cost than by the actual technical feasibility of recovering them. So the value of the material you recover has to be as much as or greater as the cost to refine it. So as you're refining it to a higher level, it's more and more expensive. And so if the material, for example, lithium, was not that valuable to begin with, the lithium is not likely to get recovered. And that has been what's happened historically. The other thing about recycling in the United States at the moment is that even if we have recycling capacity, we don't have refining capacity here, nor do we have cell production. So at the moment, even if the recyclers are recovering material here, that still has to be exported to be refined and turned into cells or cathodes. And then this is just a map of recycling facilities in the United States and Canada. And the purpose of this is mainly just to show that it is actually happening and planned to happen. I think a lot of people have the idea that the batteries can't be recycled or won't be, and that it's a like hopeless situation. At least among my friends, people seem to think that. But actually it is happening. So there are the black facilities are operating today. And then there are quite a few more larger facilities that are planned to open in the next 5 years or so. This big triangle up here is Glencore, which is a massive mining and metals refining operation. And that's currently where most of these facilities are sending the black mass or outputs of their processes. But I think at least Redwood Materials, and I want to say Life Cycle, are planning to refine and produce their own battery inputs. Okay, so generally, these are the LCA steps of doing an actual LCA. So first you define, and I'm going to walk through each of these and talk about how you might apply them to an electric vehicle. But so first you have to define your goal and scope. So the goal and scope, you would look at what the product or products are that you're studying, what the functional unit is. So I'll talk about that in a second. What the system boundary is, so what processes you're going to include in your analysis, and then what you're going to just leave out. What the purpose of your analysis is, and who is the intended audience for it. So, for example, for an electric vehicle, you could study the entire electric vehicle. So that could be like, people call that cradle to grave. So you'd study it from material extraction up until the vehicle's retired. You could also just study the battery. So you could study that from material extraction up through when the battery leaves the factory, and people call that a cradle to gate process. People also just study the impact of the cathode production, and then you also could study one of the precursors. So you could study lithium hydroxide, for example. The system, and then the purpose of your, like what your product that you're studying would depend on the purpose of your analysis. So if you wanted, for example, to estimate what the greenhouse gas benefits would be of electrifying single passenger vehicles, then you would want to study the entire life cycle assessment of the car from cradle to grave. But if you wanted to learn what was the most sustainable source of lithium, then you would study the impact of producing lithium hydroxide from ore, maybe, and compare it to producing lithium hydroxide from evaporation. And then finally, the intended audience could be a company that wants to make their process more sustainable. It could also be a policymaker who wants to know which solution is the most sustainable in the long term. And then what I'm trying to do in my research is also make it accessible to the community that lives near where the material is produced, so that they can also understand what the impacts that they're going to experience are. The functional unit for a battery, for example, this is what your so you're quantifying all the impacts, and then you have to translate it into a per unit basis. So for a battery, often this will be based either on the per kilogram, so like the impact per kilogram of producing a battery, or the impact per kilowatt hour. But one of the examples that Alyssa Kendall is like the life cycle assessment expert of UC Davis. And one of her examples for explaining a functional unit is if you were comparing the impact of paper towels to using like an electric hand dryer. And so in that case, your functional unit would be per pair of hands dried, as opposed, because you wouldn't be able to compare an amount of paper really with an amount of heat. So but that's one of the things that you have to decide when you're formulating your LCA. So the next stage is the inventory analysis. And this is where you try to take stock of what the materials are that are going into your product and what the inputs and outputs are for each step. After that, you do an impact assessment based on, for example, like how much energy you saw that it used in the inventory analysis. You'll do an impact assessment using an LCA software, and then throughout you're interpreting your results. So the inventory analysis can be thought of kind of as the accounting stage. So to do that, you want to create a bill of materials and a process flow diagram, and then map out what the inputs and outputs were at each phase. So like maybe we can do this. Actually, we can do this now. So base this, everybody on your own, just try to think of if you were going to put together a flow diagram of an electric vehicle you could define what the scope is, but you make kind of like a flow chart. So like this is the raw materials, and then you have energy. And then what else do you think you have during the raw material extraction phase? What? Yep. Okay, and what else do you think is an input during the raw material extraction phase?
Water.
Yeah. And then, so after that, you go to the cell production. So here it's probably similar, like we saw before, there's heat here. So similarly, energy, heat, and electricity, and water. And then this also produces waste. And you also have to keep track of the emissions at each step. Then you go, we'll call this a use phase. So here you have more electricity to power the vehicle and emissions. And then we'll just say it goes straight to recycling. Here you have electricity, heat, and we'll say water. So then this produces materials that can be used in cell production and also waste. So this is a super simplified, yeah. Mm-hmm. Yeah, that's a good question. That is more like these arrows. So yeah, here you have energy, and then you'll have like carbon dioxide emissions and NOx probably. And so that is occurring throughout the product life cycle. Yeah.
I don't know if this is gonna get on the rabbit hole, but system boundaries, are you gonna talk about that?
Yes.
Because like with this, you're pointing out, hey, this is truck, right? And then you can say, what about all the energy that went into building that truck? And then some truck probably had to do stuff to build that truck. So like, what about the energy to build the truck of the truck? Right?
Yeah. Yeah, that's a great point. So, and something else that's commonly left out of the system boundary is the actual construction of the facility where something is built. Because yeah, LCA can get out of hand very quickly. You're kind of constantly trying to, like, it's a lot to be wrapping your head around at once. And yeah, I think when you're drawing the system boundary, some of the things you want to think about are, like, for example, if you're comparing two products and they probably have a similar facility where they're built, you don't need to include the facility because it's not going to affect the comparison between the two of them. Or, for example, this is taken from an LCA of a battery. So they didn't include electric vehicle end of life. They didn't include the production of the actual vehicle. They didn't include the production of the battery management system, and they left out transportation. And that's basically because they were just trying to compare this certain battery chemistry with a different kind of battery chemistry. So, but this is what for a flow chart and system boundary would look like. And then over here is what the life cycle inventory could look like. And this one was comparing different papers. This is probably the most recent and I think is based on more inventory data. But so they look at the material impacts, inputs to the process. So for example, the NMs, the nickel metal cobalt oxide. This is the amount of kilograms of nickel metal cobalt oxide per kilogram of the cathode that's produced. And then, so per kilogram of the cathode, there's 0.95 kilograms of NMC and 0.38 kilograms of lithium carbonate. And then they look at the electricity that went into producing that particular component. They look at the material inputs here that went into producing each of these. And then this is what enables you to get a sense of what the overall impact is. But first you have to know how much of each material is in the battery. Okay, and then finally, when you've done all of that and you generally have a sense of how much energy went into producing the entire battery, this is where it gets very complicated because there are these really complex softwares that have databases about what the emissions are, for example, for burning one joule of diesel or getting electricity from different sources. But the impacts can be, the software can give impacts in terms of midpoint indicators. So This can include climate change and greenhouse gas emissions, acidification of the local environment, and that's related, for example, to sulfur emissions, what the land use is, what the water use might be, and what the resource use is. And then you translate those into more kind of understandable what they mean for people. So for example, the ecotoxicity is impacting the ecosystem, land use is impacting natural resources and ecosystem quality, and then human toxicity is important for human health. And these are some of the LCA impact categories that could be of interest for electric vehicles. Often it gets kind of reduced down to just the greenhouse gas emissions, and that makes sense because the purpose of the electric vehicle essentially is to mitigate climate change. However, if you're only focusing on the greenhouse gas emissions, then you're overlooking some of the more localized impacts that are experienced in areas that are producing the materials. So it's also important to look at the particulate matter formation, SOx and NOx emissions, water use, acidification, eutrophication, land use, and toxicity. Okay. So now, with all of that, I'm going to talk about one specific life cycle assessment to just kind of illustrate what this might look like. So this was a life cycle assessment that was done by researchers at Argonne National Laboratory, and they do quite a lot of this research and are sort of leaders in this and have connections with material producers and car manufacturers. So it's a pretty good source of data. And then they also release a tool called GREET that anybody can use to estimate the life cycle impacts from different batteries and vehicle technologies. But one of their more recent papers was a cradle to gate analysis of a 23.5 kilowatt hour NMC 111 battery. So does anybody remember what cradle to gate means? Do you remember what cradle to gate, what would be included if they said it was a cradle to gate? Okay. So that means it stops at the point that it's produced. So it includes material extraction, refining, cell production, and then the battery production. But they didn't look at the in-use impacts of the electric vehicle or at recycling.
That's basically what it's called. It's stopped, right?
Yeah, yeah.
And you said grade was the other one where like once the car goes, it's recycled, that was great.
Yeah, yeah. And then also sometimes people will say cradle to cradle, and that's where they're assuming that the materials recovered from recycling are being reused in another vehicle. Okay, and then here they focused on an NMC 111 battery, meaning that it was a battery where the cathode had nickel, manganese, and cobalt. And then the 111 means that by weight, the battery had an equal amount of those three metals. So as the battery chemistries are developing, producers are kind of trying to transition away from the higher cobalt chemistries, mostly just because it's expensive, also because they want to avoid the environmental and social impacts, or because they want to avoid consumer awareness of the environmental and social impacts. But NMC 111 is a pretty common battery chemistry and is kind of slowly being replaced, but it's sort of a baseline that a lot of LCAs compare the battery to. So their functional unit for this analysis was 1 kilowatt hour. So they took all of the like all of the materials that went into making the NMC 111 23.5 kilowatt hour, and then broke it down by what it takes per kilowatt hour. And that kind of enables them to compare their results to other LCAs and other battery chemistries. And the impacts that they studied in this analysis were the total energy use, greenhouse gas emissions, SOx, NOx, PM10, and the water consumption. So this is what their system boundary looked like. You can see this is just looking at the battery, and it gets pretty complex. But they include the nickel, manganese, and cobalt that went into the NMC 111 powder production. And then they also included copper, aluminum production, plastics production. This is the electrolyte. This is also electrolyte salt, NMP production. I honestly don't know what that is. The PVDF, I believe, is used as a binder in the batteries, and then graphite for the anode. So those were all of the materials that they looked at the impact of producing to go into the cell. And then they also looked at other parts of the battery pack, so steel, insulation, coolant, and electronic parts. And then finally, they looked at the impact of assembling the module and the cell. Okay, so what they found was that the NMC powder was the most significant contributor to the overall environmental footprint of the battery. So it contributed nearly 40% of the total energy use and greenhouse gas emissions, and then 63% of the sulfur emissions and 30% of the water consumption. This also, I think, gives an indicator for, this is what most LCA results and papers look like. And it's, I think we have a lot to learn about conveying results clearly in this field. But here, so you can see this bar is representing how much of this impact the NMC powder produced. And then these are the other uses. So you can see aluminum was a pretty substantial contributor of water use, and then NMC also contributed most of the particulate matter, NOx, SOx. The other areas that kind of dominate the environmental impacts are cell production for the energy use, and that goes back to the humidity control in the production facility. And yeah, what else is interesting about this? Oh, Alan, going back to your point, you can also see here, this is just the weight. So this is just kind of the material composition of the battery. So, and here you can also see that the NMC powder is a much smaller percentage of the battery by weight compared to what its impact is. But you can see that the copper is here, so it looks like it's about 10% of the battery overall. Oh yeah, go ahead.
I have a question about the possible graph.
Yeah.
So I get the CO2e, the CO2 produced, and that kind of stuff. But like, where are we getting like 752 liters, for example, for water? So like, where's that number coming from?
Yeah. So basically, what they did was quantify the amount of water that is consumed during all of these stages here. And then they normalize that by the per kilowatt hour of the battery. So this is to create the entire battery, and then this is the impact per kilowatt hour.
kilowatt hour battery, is it fair to say, let's say if you wanted to find the total impact of a 70 kilowatt hour battery?
Yeah. I think maybe the pack materials would be bigger. But overall, yeah. Okay. So there are several factors that can affect what the life cycle impact is, in addition to what the materials are. So one of them is a really critical one is the geographic region. So this is pretty intuitive if you're thinking about where the car is driven. So if you're driving an electric vehicle in California, the life cycle impacts are going to be much less than if you're driving it like in Chicago or somewhere in the Midwest where they have more coal in their grid mix. But the electricity mix also matters in the region where the battery is produced, particularly for parts of production that use electricity as opposed to heat. And then another thing that influences the life cycle impacts beyond greenhouse gas emissions is where the metals are sourced from. So for example, with nickel refining, there are certain measures that can be taken to capture some of the sulfur emissions and scrub it. But those are not necessarily practiced everywhere. So nickel that is sourced from Canada is probably going to have overall a lower sulfur oxide emissions impact compared to nickel that's sourced from Russia. Other factors that affect the life cycle impact are the facility throughput, just because the amount of energy per battery produced is going to be lower if you're producing a lot of batteries at the same facility. And then also, like was brought up, the shipping distance. So another thing people talk about in trying to make batteries more sustainable overall is trying to co-locate more of the supply chain. And in the US, people are talking about that also in terms of retaining control of strategic minerals. Mm-hmm.
Okay, so we talked about this last class, and I'm kind of curious. So in 3, the way to calculate the emissions is attributional. Okay?
Mm-hmm.
And so we talked about attributional versus consequential emissions, and so I'm kind of curious where you stand on that.
Yeah, it does get very complicated when you're kind of speculating about what would happen, if something were done or not done. And I think because my research is more focused on the impact in a specific place, I think I am more familiar with attributional LCA. But I think when you're doing a more high level comparison of the broader impact of a technology, it's important to use the consequence of how something might have been produced if it weren't for the process you're modeling. That does kind of get into recycling. So how do you guys think you might capture the impact of recycling in an LCA? Mm-hmm. Yep. Yeah, that is exactly right. So essentially, first you calculate the impact of the battery recycling process, because the recycling processes also require a certain amount of heat and electricity and water and are associated with their own emissions. So you estimate the impact of the recycling process and then calculate the net benefit by assuming that you're avoiding that impact from producing raw materials. So this is some of the factors that influence the overall benefits of recycling are what the recycling process is, first of all. So I talked about hydrometallurgy earlier. The other main commercially available recycling process is pyrometallurgy, and that's essentially where the batteries are smelted and melted down, and then different constituent metals can be isolated through a chemical processing. But those processes has different impacts because the hydrometallurgy requires energy and generally environmental burden mostly to synthesize the chemicals that you're using. And then there is also some amount of heat and electricity used at the facility, whereas a pyrometallurgical recycling requires extremely high temperatures and has generally a higher energy consumption.
How do you deal with certain materials that are like effectively recyclable? Like, how do you decide kind of the recycle if you want to do like what portion you want to
Yeah, that is a good question. I mean, with aluminum, I think you just assume that 100% of the aluminum is displacing a virgin material. With the cathode powders, I haven't seen a life cycle assessment that was assuming that anything would get recycled more than once. So I think in general, it's kind of, people tend to just limit it to the one-time recycling and whether that's, and assume that that's going to displace virgin material. But it would be interesting to see how it might affect the results if you're assuming it's going to get recycled multiple times. Yeah, so the other factors that influence the benefits of the recycling are the battery chemistry itself, because that impacts how energy intensive and burdensome the materials that you're displacing were. So for example, here, this is calculating the net benefit of recycling in terms of the carbon dioxide equivalent emissions. And you can see the NMC and NCA, which is nickel, cobalt, aluminum, both generally have a positive impact, whereas the LFP battery, which is lithium iron phosphate, is actually not avoiding carbon dioxide emissions through the recycling process. And that's because lithium iron phosphate metals are generally not as energy intensive to produce. Importantly, this study only looked at carbon dioxide emissions. If you also included the sulfur emissions, the benefits of recycling are much more dramatic because you're avoiding a lot of emissions from smelting and refining. So this is one area where the focus on greenhouse gas emissions doesn't fully capture the impact. Again, the location of where the batteries are being recycled influences the results, and that mainly just goes back to the grid mix in the facility. Okay, so essentially the conclusion of all of this is that internal combustion engine vehicles have lighter production phase impacts than the electric vehicles, and partly that's just because the vehicle itself is lighter, but it's also because the battery materials themselves are intensive to produce. However, the internal combustion engine vehicles have higher emissions in the use phase and overall higher global warming potential. Meanwhile, internal combustion engines, I didn't really talk about this, but there is actually a pretty robust network for recycling end-of-life internal combustion engine vehicles. In the US, it's almost entirely market driven, and there's a pretty big network of auto dismantlers that take apart cars and resell the parts. And then the aluminum and most of the body can be recycled by scrap metal recyclers. Whereas for an electric vehicle, it's just much more complex to recycle the battery because you have to shred it and you have to separate, the aluminum and the copper and the black mass. And they're also more difficult to handle because of the fire hazard, and they're extremely high voltage batteries. So it's just kind of a more, it's like, as I showed earlier, they can be recycled and probably will be, but it's just much more complex than in recycling an internal combustion engine vehicle. But overall, as long as they're not fueled with coal, they have lower greenhouse gas emissions when you look at the life cycle, and that's expected to decrease pretty steadily as the grid becomes decarbonized. However, there's the higher toxicity from production. So one of the main solutions to this is to making the life cycle less environmentally burdensome is through the circular economy strategies, like making sure they're reused and recycled at end of life. But there's also initiatives to make the material extraction itself more environmentally friendly. So one initiative is the Global Battery Passport, which is a blockchain technology. And the hope with that is that it will enable more tracing. So battery producers and car makers will be able to trace where their materials were sourced from and kind of what the labor practices and environmental mitigation measures were that were used there. It's also important that as we are extracting new materials, that the communities who live nearby are involved and have some say in whether they want the extraction to take place and are aware of what the impacts are. And then finally, in California, there was a bill, I want to say it was SB 366, that's going to require automakers to source their lithium from California, assuming that it does get produced in California. But policies that require material sourcing from certain regions or require materials that are produced using recycling are kind of another mechanism to make the overall life cycle more sustainable. And then finally, electric passenger cars are just one type of electric vehicle. There are also electric bikes and electric buses. And if you look at the impact and the amount of battery required to transport one person, they're significantly less material intensive. So that's another important thing to keep in mind. And that's it. That's all I have. Yeah.
So going back to the previous slide, you said that there are other forms of electric vehicles of just your typical moving car.
Mm-hmm.
What do you know about electric bikes? One thing that we haven't talked about yet in this class is electric bikes and their impact and stuff like that. And I was just curious, like, is there like mass research on e-bikes, like
bikes or
like this kind of thing?
I mean, I know that I know BMW is producing them, and there are other yeah, but I don't know. Yeah.
Yeah, because I was saying like the main thing that I know is that I know like maybe 5 or 6 that I can like think of people I've ever seen on e-bikes, and I know that like in the community they're not like super, like not a lot of people who have been riding a long time like e-bikes because they don't make noise.
Right.
And it's kind of funny, but like noise is one of like the things that like, oh, that's what freedom feels like.
Yeah.
People think about riding bikes, but I don't know. I was just interested.
Isn't Harley Davidson coming out with a whole line of electric?
Yes, they are actually, yeah. And so I don't know what the public perception of that would be, but I mean, yeah, I do see quite a few e-bikes around campus though, because you can't compare them by.
Right.
Yeah,
yeah, no, I think from a safety perspective, the idea of a essentially silent motorcycle is concerning to me, but I'm a big fan in general. Like, I think I would like it if more people were on motorbikes and not cars, because it's a much lower impact whether you're fueling it from gas or from a battery. Well, yeah.
One of the form factors that's really common in China
Right, mopeds, yeah, actually,
It's
that's like the way to get around.
Yeah.
Mhm.
So if you think of that as like a commute mode, right, or is it just like, oh, you want to get from point A to point B? It's like one of the most, you don't have to lug around a 4,000-pound car, right? And I think electric versions of mopeds are like exploding.
Definitely.
Yeah.
I feel like in other countries, like whenever you see videos of like another country and like it, like you know, like those like any documentary, like it opens up with like the streets of whatever city that is, and it's just like
Mhm.
mopeds everywhere.
Yeah, and another thing that I know they do in China that they don't do here as much as I know is they have walls for battery packs where you can just swap out your battery pack and plug it back in and take a charged one.
So there is battery swap.
Yeah,
Not here.
yeah,
Talking about like the concern for safety and silence. And I'm thinking I'm like worried about the rider. I
yeah,
mean, instantaneous torque on a vehicle that can do a wheelie and backflip is probably not what you want to do. So it's never been a motorcycle.
yeah.
Think about that too,
Yeah, no, I've mostly thought about that for myself because like given what I study, it seems like it would be the most on brand way for me to get around. But yeah, it seems like it could. I don't know. Because I also, when I'm driving and a motorcycle approaches suddenly, I think it would really be quite startling if I had no sound or warning. But yeah, I don't know of anybody who has studied that. I think most of the studies on things like e-bikes are more about vehicle miles traveled and also safety and like parking and charging and stuff.
There is a lot of research on e-bicycles.
E-bicycles.
Yeah.
Not so much on
Yeah, like the gym bike.
Yeah, honestly, I don't know about a lot of research that's about motorcycles generally. I think, yeah, we need more representation of,
You want to get a
Yeah.
school, do a bunch of research on motorcycles.
There's definitely plenty of opportunity.
Yeah.
yeah.